Hey everybody, and welcome back to Algebra 2 Online. So today's video is really going to be focused on just looking more in depth at hyperbolas. There's going to be a few important facts that I got to talk about, and then just got a few little questions that are kind of like trickier, kind of problem-solving based hyperbola questions. So to start though, just kind of pulling back from something in the last video. We have one of these conic sections that's written in this form, and we want to turn it into like the standard form where we can see like the center and know the like A and the B values, so we can like sketch whatever it is. So this is one where basically you have to complete the square, right? And we have some X things here, we've got some Y things, we got a number. Again, we don't need the numbers, so we can kind of move that over. But we want to group these X things together, and then we're going to add something there. We'll just kind of leave it blank for that. And then we have these Y things, 4y squared minus 8y, and again we're going to kind of add something there, and then this has to equal 59 if you move the minus 59 over. So one of the very first steps, though, of completing the square, and this is a very, very common mistake here, that because we just don't see it too often, I said you have to have A be 1. If you go back and look at that video on completing the square, A has to be 1 for this whole trick to work. So we have to take the 9 out of this group, and we have to take the 4 out of this group. So that's the first thing actually I'm going to do to complete the square. So we have x squared minus 6x, and then plus something in there. And then we're going to take a 4 out of here. Y squared minus 2y plus something is 59. And then just normal old completing the square stuff here. So we want to divide this by 2 and square it. So we're going to get 9 as my magic thing there. And then here we're going to divide negative 2 by 2 and get negative 1. Square it, we're going to get 1. So those two are my perfect squares. And again, I'm going to have to add 2 numbers to this side in order to balance this equation and make it a true statement, like not change anything. But if you look at what I have here, right, I have 9 times 9. So I actually have to add an 81. And then here I have a 4 times 1, so I really added a 4 on this side. So I have to add 4. So this line is the same thing as like what I started with now, okay? But it lets me factor it, so into a perfect square. So x minus 3 and x minus 3 is how that factors. Then y minus 1 and y minus 1 is how that factors. And then if you just add up the right-hand side, you get, whoops, that should be equals. What is that, 144? And then, that's more or less the form I wanted in, but it's a little bit nicer if we set this equal to 1. And so we'll just divide by 144. And so we would have 16 on the bottom here, right? Because 9 times 16 is 144. And then likewise, if we divide 144 with the y term, we'll get a 36 on the bottom, right? Yeah. 36 times 4 is 144. So this tells me everything I need to graph this thing. So the center is the opposite of those numbers in the parentheses. A is the square root of 16, which is 4, and B is the square root of 36, which is 6, right? And so then I can go ahead and I can graph it. And you should also see what kind of conic section this is. So, these numbers are both positive, these scalars in front. So it's an ellipse, and 16 and 36 are not the same number. That's another reason. That's one of the reasons it's an ellipse. If these had both been like 16s, it would be a circle, right? But basically we're stretching it more in the y than in the x. And so it's an ellipse, like a vertical ellipse. So I'm just going to go ahead and plot 3, 1. And then A is my left and right movement, so I've got to go 4 units left and right from there. So here, and then 3 plus 4 is 7, so over there. And then B is 6, so from the center go up and down 6. So we got that point right there, and then this point up here. And so really that is like enough of the graph. You don't need to really add any more points. You can just try to draw in as best as possible an ellipse. And really this isn't part of the graph, the center. So it's actually good to take the center out because the graph is just this outer region right here. And that's it. That's how you could graph that conic section. All right. This question seems kind of odd, and you'll see where this is going, I hope, in a second here. So what I have right here is, actually it kind of got cut off, I just realized. So this is a square root around that whole thing, and that's a squared in there. And so this right here is kind of like a line. I put it in quotes. And it'll really look like a line if you think about this limit question. So if you think back to when we talked about limits, the idea here is we want to know what this looks like when x is way out at infinity, okay? And really the question is, what is just the slope of this, like in quotes, line when x goes way out to infinity? And one thing that's going to happen here, if x is really, 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 really big, right, and a and b are just like constants here, so let me just kind of write that. So a and b are just part of the real numbers. We'll just do that. And so if you have just constants for a and b, but this x is allowed to grow really, really, really large, then this would certainly just go to 0 because whatever a is, it's just fixed value of a, and you divide by larger and larger and larger things. And so this thing right here, right, is going to go to 0. And then you literally would just reduce this to y equals b over a x square root of 1, which is just b over a x. And so the slope of this line, right, is basically just b over a. So this is actually a very important result related to a hyperbola. And this is actually, weirdly enough, an equation of a hyperbola. And I want to kind of show you that now. So what I'm going to do first to turn this into a hyperbola, I am going to square both sides, okay? So we have y squared equals b squared over a squared, x squared, and then if you square the square root, right, it's just gone. So we get that. And then I don't like fractions. I always tell you guys to try to get rid of fractions. So I'm going to multiply by the a squared, I think. And then I will probably go ahead and just distribute into the parentheses. And the x squareds would, of course, cancel, right, in the last multiplication there. And so now if we just go ahead and group the x and y terms on the same side, it'll start to look a little more like a hyperbola. So I'm going to move the b squared a squared thing, then minus 1 to the left, and then minus the y squared a squared term over here. And then I'm just going to divide by b squared a squared, right? And I will, of course, get 1 equals x squared over a squared, and then minus y squared over b squared, right? In this one, the b's are canceling, but then in this one, the a's are canceling. So this is our standard form for a hyperbola. And the purpose of showing you this is that hyperbolas actually have an asymptote. There is a line that plays an important role in all hyperbolas, and the line, the slope of that line is b over a, or actually it can also be negative b over a. And I have a picture on the next slide I'll show you. But basically all we just did is we took a weirdly written hyperbola, which really is a hyperbola, but it's just when you write it like this, it kind of looks like a line. And we were thinking about what happens to this way out at infinity, and it looks like the graph sort of approaches this line that has this slope b over a. And that's actually true for any hyperbola, no matter what a and b are. So it's really this picture I want you to see. So no matter what hyperbola you have, whether it's one like this or one that would be like up and down like this, the slope of these like asymptotes that are in the middle that we don't normally see, they're not really part of the graph, but this graph is sort of bounded by one line that is literally just whatever b is and a is, it's just b over a x, and then this other one is minus b over a x. And these asymptotes will be really what we use to help us graph hyperbolas. They have to go through the center, okay? And then basically what we do to graph a hyperbola is we kind of plot the center, we put down these dotted lines, and I do want to see those. And then you'll just use the a or the b values to measure, out, left or right or up or down. And then you'll plot these vertex points, and then you'll kind of just fill in a curve that like approaches. You'll just, you'll fill in a curve that approaches these dotted lines, okay? And I'll show you some examples of some in a bit. Just a few more kind of key, definitions and facts and things I want you to know. So remember, there's two types of hyperbolas. When the y1 is negative, it's basically a left-right hyperbola like this one. So when you see, I guess I'm just going to write like this. The positive term dictates the direction. And so here, this one is going to be a sideways one, but here the negative x and the positive y means that it's one of these hyperbolas. So you can always get a left-right one or a up-down one. And a and b are still the same thing they kind of were for ellipses and everything. A is the distance from the center, like left and right, out to the vertex point there. If it's one of these, you can really plot those vertex using a and b. If it's an up-down hyperbola, then b is just the distance from the center out to the vertex, okay? And the asymptotes always have a slope of plus or minus b over a, and they always go through the center, okay? So you basically will plot these lines before you actually do the graph. And then this is just kind of the important definition stuff. The transverse axis is always the one that has the vertices, and its length is either 2a or 2b. So here, this is an example of one where the transverse axis is 2a. This is a and this is a, so it's 2a. And then the conjugate axis is the one with no vertices, and it also would have a length of 2a or 2b. It just depends on if you have one of these hyperbolas or these hyperbolas. All right, so I do expect definitely that you know these definitions. They're important to know. Basically, transverse, one with vertices, conjugate, no vertices, okay? And transverse can sometimes be the vertical one if it is just one of these kind of hyperbolas, okay? So let me show you how we would go ahead and graph one of these hyperbolas. So I'm going to do this question where I want you to write down the equation of the hyperbola. It has two asymptotes with slope plus or minus 5/3. one vertex at 0, 5, and the hyperbola is centered at the origin, okay? So the probably the first thing I'm going to do, I mean, the center is at the origin, and we know these two vertices, or sorry, these two lines will basically just go through the center, and the graph that we will sketch will basically bound to those two lines. It'll be kind of stuck into certain quadrants that are formed by those two lines. And so the slopes of the asymptotes are 5/3 or negative 5/3. So we're just going to go up 5 and over 3, which is right there for one of them. And so one of them is this line. And then the negative one is just up 5 and to the left 3. So right here. And then we get that line. And we were told that, one vertex is at 0, 5. And so that's right there. So we know that this distance right here is 5, and we have to go 5 units the other direction as well in order, this is a very symmetric graph. So our other vertex is right there. And then literally for graphing these things, you need to have these asymptotes because all I'm expecting, I don't literally expect any other points to be shown except these 2 points. You just want to show me a graph that's kind of bounded by these 2 lines for this little part, and then these little parts down here for this, okay? Asymptotes are these things in math that we can get really close to, but we never cross. And that's exactly, what I'm trying to show right here. So this hyperbola is like getting really, really, really close to these 2 lines. And that is enough info to also write the equation, right? We know the center is the origin, so there's no like shift on the x or the y. And we know that it's a open, like up and down one. And so that means that the y is the positive and the x is the negative one. We know this distance is 5, and that's a b, right? This distance right here is b, and it's 5. And so what we actually put down here is the square of b. So we're going to put in 25. And then, we need to know a. And what we do is we can use this fact, let me go back here, this fact that the slope of the asymptotes are b over a to get a, right? So we just need, let's see, what color do I want to do? We need 5 over 3 to equal something proportional to 25 Sorry, this one's really simple. I'm thinking of the next question. So here, we know b is 5, which means that a is literally 3, right? And so we don't even need to do any proportion stuff. If we have the slope of 5/3 and we got b is 5, then this literally just has to be 3 squared. So that's just 9. And so that's it. So that's the equation of this hyperbola, and that is literally what I expect for a sketch of it. All right. So this question takes, I think, a little bit more thinking here. So then this is the one where you're going to need to do some kind of proportionality argument to figure out A's and B's here. So I want to just write down the equation of the hyperbola that's shown in this picture, right? These are your asymptotes for the hyperbola. You've got your center. You got a vertex point here. But we've got to figure out, an A and a B, and then that's really the main work in the problem, because the center is really fast, right? We can just do x minus 1 squared. We got y plus 5 squared. And, it's pretty clearly it's a left-right one. And so the x thing is positive, so my negative will go with my y term, right? But the trickier part is the A's and the B's. One of them, to be fair, is not that bad, right? Because you have this measurement right here. And if you just count, this is 5 units plus 1 more is 6, and that is an A, right? And so I'm going to put a 36 in down there. But the B takes a little bit of thinking, okay? So if you do the whole slope thing here on these asymptotes, right, the slope of that is actually also 5/3, right? If you go up 5, you go over 3 to here. So this is 5, this is 3. So the B over A slope thing here is like 5 over 3, but A was 6, right? And so you have to think, what would I put in for B that is still proportional to 5 over 3, right? And, hopefully it's not too hard to think about. You just times by 2 to get to 6. So we need to times this by 2 to get to our correct A value. And so 5 times 2 is 10. And so, our correct B value. So B just has to be 10 because it needs to be proportional to 5/3, which is the slope of this. And so if this is 10, my B, then what I put in here is 100, right? And if you truly plug this in to Desmos, you will see this exact graph. And there is a little 1 there. Right? So that one's a little weird, but basically a lot of times we use this slope of the asymptotes to help us solve for those A's and B's. One of them you can usually see really quickly and easily from the graph because you can just kind of count how many units that is. But the other one you have to usually think about a little bit. All right. Just one more question I want to do here. I want to write the equation of the hyperbola that has asymptotes x minus 2 and 6 minus x, and a vertical transverse axis of 8. Okay. So probably the first thing I would do, and I'm also going to graph it. So the first thing I would do is I would just graph these lines, right? So for x minus 2, we've got a y-intercept of 2. Nope, we don't. Sorry, we have a y-intercept of negative 2. And then the slope of 1. So we got slope of 1 here. So that's one of my asymptotes. And then the other one has a y-intercept of 6 and a slope of negative 1, right? So here's my negative 1 slope. And we know that the asymptotes have to intersect at the center, right? So actually this tells me one of the things I needed for the equation of this. So I now know the center is at 4 in the x, so x minus 4. And then up 2 in the y, so y minus 2. And then I guess we can put in a little bit of this other stuff. We need to still know, is this the positive one or is this the positive one? We also need to, of course, know A and B. And that is what we can get from this fact. So I say that the transverse axis has a vertical, I need that too. Vertical transverse axis of 8, okay? So if you go back to the definition of a transverse axis, so the transverse one is the one that has the vertices. So that means that my hyperbola is actually kind of like this picture. It's one of the open up and down ones. So that means that the y term is the thing that's positive, okay? And the transverse axis, since it's an open up one, then that's going to help me get B. So where's that question? So I basically know that 2B, right, is 8, and so I know B is 4. And I now know that this is a positive y term, negative x stuff. And then if B is 4, I'm going to put 16 in there. And so you're really close to getting the equation, but we just need to use the B over A thing. So we know the slope of these lines is always B over A. We know B is 4, but I don't know A, right? And luckily, we know the slope of the asymptotes. We are given that. The slope is 1 or -1, right? And so this has to equal 1, right? And the only way that this is ever going to be equal, then, is if B and A are the same thing. So you basically have, what color do I want to use? Let's just do orange. So basically A has to be 4. And so if A is 4, go up here, put in the 16. So this is a, just literally knowing 2 facts about the hyperbola, I was able to write the equation of it. And I should also graph it. I was asked to graph it here. So for the graph, I would just go ahead and plot, we already have the center really, but we know it's an up and down one, and we know B is 4. And so if I'm at 2, I need to go up to 6. And I also need to go down to -2. And then, let's actually use a different color here. I don't know, do purple. So then you just want to show something that gets close to these asymptotes, okay? So just something like that and that. A little bit cut off the page, but you get the idea. So this is kind of a trickier, weird question that you'd have to do some problem solving on, but it's a good example of the kind of stuff that we're going to be doing with these.